Before we discuss the development change and challenges of optical communication, let me guide you through the history of optical communication first. Optical communication is a general term for all communication modes that use light as carrier to transmit information. Optical communication can be traced back to the beacon towers 3,000 years ago, and later the flag language of the Western seafaring era, modern traffic lights invented by the British, and so on. Whatever it is beacon towers, banners, or traffic lights, they are different forms of optical communication. They have one common point. All these methods use the atmosphere to transmit visible light and receive it by our human eyes. So the implementation is relatively simple and information transmitted is not so complex. Therefore, they can only be regarded as primitive optical communication. While optical communication in modern sense generally refers to the optical fiber communication, it is a communication mode that relies on optical fiber as a medium to transmit information. In 1953, Narendra Kapani, who worked at the Royal Academy of Science and Technology in London, developed the cladding fiber. However, the optical fiber in the early stage has a large loss, of which the attenuation per kilometer can be as high as to 1,000 decibel. Therefore, it is impossible to use it to communicate. In July 1966, Dr. Carl Kuhn and Hockham of the United Kingdom's Institute of Standard Telecommunications published a paper of great historical significance on the future of optical fiber transmission. This paper analyzed the main reasons for the high loss of glass fiber, and boldly predicted that if we could reduce the impurities in glass fiber, it is possible to reduce the optical fiber loss from 1,000 decibel per kilometer to 20 decibel per kilometer only. This can be used for communication. This paper also inspired many scientists to work towards low-loss optical fiber. In 1970s, Dr. Capron of Corning Glass Company, which is from United States, together with his colleagues, after many tests, finally developed the optical fiber with a transmission loss of only 20 decibel per kilometer. This is the world's first low-loss quartz fiber. This amazing move marks the elimination of the last obstacle to the application of optical fibers in the field of optical communication. By 1979, the attenuation of optical fibers has been reduced to 0.2 decibel per kilometer. In the 1990s, SDH equipment became the mainstream optical communication equipment. Later, at the end of the 20th century, a large-scale construction of 2.5 gig DWDM systems began, and optical communication entered the WDM era. In 2003, the home broadband network also met its milestone. The GPON was standardized, and the fiber-to-the-home service developed rapidly all around the world. In 2011, the 100 gig coherent optical technology was successfully put into commercial use, marking the advent of the commercial era of coherent optical communication. It opened the stage for capacity upgrade. 100 gig system was successfully deployed, and the 40 gig system was eliminated due to its cost and efficiency. And in 2015, the CDCF ROADM technology was put into large-scale commercial use for the first time, ushering the all-optical switching era. In 2018, the world's first optical cross-connection network was put into commercial use in China, meeting the scheduling requirements of nodes with ultra-large traffic. Three-dimension WDM networks has become a trend, ushering the or Optical Network 2.0 era. In 2019, Huawei launched the Super C-band 6 THz ultra broadband transmission solution. Spectrum utilization in optical communication networks has entered a new phase. In 2020, the single wavelength 800 gig transmission optical module was released and commercialized. The commercial system capacity has reached 48 terabits per second. So in the preceding slides, we have introduced the history of optical communication technology. Next, let's look at the current status of optical communication technologies. Develop bottlenecks and vision of optical communication technologies by 2030. First, it is the current state of optical communication technology. Optical communication technology is widely used in terrestrial networks. The terrestrial networks including 4 scenarios. First scenario, it is the backbone network scenario. WDM backbone network needs to provide high bandwidth and low distance service transmission. In most carrier backbone networks, the single wavelength 100 gig system is the mainstream solution. In the past 2 years, more and more carrier backbone networks has adopted the single wavelength 200 gig solution for network construction. It provides a single fiber capacity up to 16 terabits per second. It can meet the increasing data center, remote interconnection, and large video traffic requirement. The second scenario is the metropolitan area network. With the growth of new services such as 5G and 4K video, the network bandwidth requirements surge. The metropolitan area network ring capacity is mainly 200 gig and 400 gig. It also needs to provide multiple types of interfaces to access various types of services. For example, Fast Ethernet and Gigabit Ethernet interfaces are used for small and medium-sized lease lines. 10GE and 25GE interfaces are used for IP RAN or SPN access. SDH interfaces are used for traditional high-value lease line services for the government, for the military, and financial industries. The third scenario is the access network. Currently, with the acceleration of home broadband, the fiber to the home coverage rate continues to increase. Currently, the access network products are mainly GPON. However, in the past 2 years, 10G-PON has also been developing. The proportion of the network development has been increased to over 10%. The fourth scenario is data center interconnection. In intracity active-active DC scenarios, daily data needs to be synchronized every second. Therefore, high bandwidth is a major requirement for data center interconnection. The high bandwidth of a data center is reflected in 2 aspects. Large capacity switching. The core nodes can support 12.8 terabits electrical layer switching. On the other hand, the port density can reach 3.2 terabits per unit. In addition to the terrestrial network, the optical communication technology also has a special scenario, the non-terrestrial network. Inter-satellite optical communication. This is a direction that we need to pay special attention to besides the traditional ICT field. Inter-satellite optical communications. Here it's not the communication between different planets, but it's the communication between satellites and the ground. For example, Musk's Starchain project, which has been highly exposed in recent years. It is one of these projects. The current terrestrial optical communication network can only provide coverage of 5% of the Earth's surface. In many sparsely populated inland areas, as well as ocean-going ships, fishing boats, offshore drilling platforms, and the civil aviation, broadband access and information interconnection cannot be implemented. Intersatellite optical communication is mainly applied to mobile services and fixed services. This solution mainly solves the network access problems in the preceding scenarios. Currently, this solution is still in the initial stage. Now we can understand the current situation of optical communication technology. Next, let's learn about some bottlenecks in the development of optical communication technology. We still follow the previous logic. Optical communication networks are classified into terrestrial networks and non-terrestrial networks. Terrestrial networks are classified into 4 scenarios. First, backbone networks. As 5G services enter the mature stage, network bandwidth requirements continue to rise. When we are pursuing higher bandwidth and long-distance transmission, backbone networks have almost reached the theoretical ceiling of Shannon's limit. If we want to continuously increase the speed, we need to have breakthroughs in basic series or find new gain materials to expand the available optical spectrums. The second scenario is the metro network. Large video service traffic and 5G base station densification deployment require the metro network to provide low-cost connections and use silicon photonics. New packaging technologies and new material platforms also need to be used to achieve low cost. In addition, to achieve miniaturization and reduce the space occupation of the equipment room, photonic integration technology is a research direction. The third scenario is the access network. The network bandwidth is restricted by the power budget and cannot be increased. On the other hand, to optimize the delay, the original TDM mechanism needs to be reformed. The last terrestrial network scenario, it is the data center. The bottleneck of the data center includes 2 aspects. Capacity is limited by power consumption, and port density is limited by integration and heat dissipation. While for non-terrestrial networks, intersatellite optical communication is more faced with the cost problems. Satellite internet needs to improve communication rate, the large-scale networking capabilities, and reduce power consumption and make the size smaller. These are the main challenges for the non-terrestrial networks. Looking ahead to 2030, if we can break through these bottlenecks, the prospects of optical communication technology and industry in the next decade are very bright. First, with the ultra-wide spectrum of 400 nanometer and ultra-high single wavelength rate of 800 gigabits per second or even up to 1.6 terabits per second, the backbone network can achieve 100 terabits per second capacity. The metropolitan area network will use optical electrical convergence platform to provide ultra-reliable connections with quantum encryption and microsecond level stability and low latency services. For access network, a new P2MP architecture will be deployed on the access network to achieve 200 gig high bandwidth access and 1 microsecond ultra-low latency. Last one, for data center network, all optical switching with a capacity of P bits per second, fast port switching at the nanosecond level, and doubling of port density without changing power consumption. All these will come true. On the other hand, the non-terrestrial networks increases the inter-satellite communication rate up to 100 gigabit per second, achieving the fiber-like experience. Satellite cost will be reduced through lightweight development. Large-scale engineering deployment will become reality, and ultra-reliable rerouting assurance services can be provided for the users. Lastly, let's have a brief summary. In this chapter, we discuss the development history of optical communication technologies, from Dr. Gao Kun's optical communication theory to the invention of practical optical fibers, from SDH to WDM to ROADM, optical cross-connection to super C-bands, until recently the commercial use of a series of new 800G technologies. I also share the current status of optical communication technologies in different scenarios. We discuss the technology bottlenecks and also the vision for 2030. The terrestrial network is classified into 4 scenarios: the backbone network, metropolitan area network, access network, and data center. The backbone network needs to evolve to a higher bandwidth and a long-distance network. This requires the breakthrough in basic theory. The metropolitan area network needs to continuously provide multi-service access and provide low-cost solution. Access networks continue to evolve to high bandwidth and low latency. This requires innovation in network architecture. In the data center scenario, ultra-large switching capacity, ultra-high integration, and low power consumption are the objectives for future evolution. That's what we have covered in this section. Next, let's consolidate this section with 2 questions. First, it is a single choice question. Which of the following is the correct sequence for the development of optical communication technologies? We have mentioned this topic when we introduced the development history of optical communication technology. The main point is that the invention of fiber was even earlier than the theory of optical fiber communication. And also, ROADM is the foundation of optical cross-connection. So the correct answer is C. Optical fiber invention first, then the optical fiber communication theory. After that, it is the SDH, and then WDM, ROADM, GPON, optical cross-connection, and super C-band. Finally, it's the single wavelength 800G technology. The second question is a multi-choice question. So, what's the development chain of optical communication technology? A. 100 terabit level single fiber large capacity. B. Service encryption, ultra-high reliability. C. Access network 200 GPON high bandwidth. D. Data center P-bit single fiber large capacity per second. E. Inter-satellite communication rate 100 gigabits per second. So this question is actually quite simple. The answer is A, B, C, E. Option D, it should be P-bit per second large capacity switching in the data center. This is not the single fiber P-bits per second capacity. Well, that's all for this chapter. Thank you.